Welcome back, folks, to the Get a Grip on Lighting podcast. On today's podcast, we have a couple scientists. First, we're going to talk about Jakoah Brgoch. He is an associate professor in the Department of Chemistry and a principal investigator in the Texas Center of Superconductivity. Jakoah also has a courtesy appointment in the William A. Brookshire Department of Chemical and Biomolecular Engineering, and he is a member of the Hewlett-Packard Enterprise Data Science Institute. He completed his bachelor's and master's in chemistry from Illinois State University, followed by a Ph.D. in chemistry from Iowa State. Following postdoctoral research at the University of California, Santa Barbara, he joined the Department of Chemistry at the University of Houston and is now leading a multidisciplinary research group through a combination of material synthesis, characterization, first principles computation, and machine learning. His social media and that can be found on the Get a Grip on Lighting website. And we're also joined by Shruti Hariyani. She completed her Bachelor's of Science and is in the process of a Ph.D. in Inorganic Chemistry. So she's smart. At the University of Houston under the supervision of the fellow we just talked about. Her research is focused on the discovery and characterization of novel phosphor materials through experiment and computation. But before we go there, Greg, we got to go to the gangsters down at SATCO. Go to SATCO. That's SATCO Light, SATCO.com. That's SATCO Light Thing, right thing, Greg?
Yeah, you're right. And, one thing about SATCO is they've been around a long time. I've been in lighting a long time, and I learned something new about them all the time. I had a customer who asked for a double basket troffer fixture, where it has the two lenses.
Yeah, sure.
I don't see those ever, but guess who has them? SATCO 2x2, 2x4. They have their starfish as well. They have a security light with a camera, very much like those ring systems that people have, but it's SATCO and you don't pay for it. It's all part of the Starfish app. Nice system.
I was just on there today and found a 72-inch LED tube bypass.
Perfect.
There you go, right? So go to SATCO.com. That's SATCO, the Gangsters of Lighting, and of course the National Association of Innovative Lighting Distributors, where it all started. Folks, this is going to be America's Lighting Convention, Greg Eric, coming up in Dallas in September. Yeah, it'll be here before you know it. So go to NAILD.org. Welcome to the show, Shruti and Jakoah. Thank you for joining us.
Thanks for having us.
Yeah. Let's start it off here, guys. University of Houston, what are you working on with LED? It looks like you're doing a lot of things, but what specifically on LED lighting?
Yeah, so my group is really, we're chemists and material scientists by training. So what we're looking at is not product development, but how do we make new materials that go into everything that you guys are seeing, that you guys are selling? How do we take new materials and make lighting that is more efficient, higher color rendering, higher color quality? And then more importantly, how do we do so in a way that we can make materials cheaper? LED lights are still pretty expensive, and a lot of that is that the process to make the luminescent materials, it's not horribly cheap. There's a lot of intellectual property challenges that drive the price up. So how do we make materials that are less constrained, that we can get into more houses and commercial placements?
The question I've got, I guess, is let's start off with the materials of an LED right now. What are the materials, and then what are the potential materials that you guys are working on?
Yeah, so the most common LED materials today, there's really only a handful. So if you're going to go to the store and buy an LED light bulb, they're all based off of a blue emitting LED chip. So it all starts from this sort of core blue emission that comes from an indium gallium nitride semiconducting chip. So the way that the semiconductors work, they essentially apply your electrical current, and then you get electrons and holes that separate out. And as these things recombine, they emit the photon with blue energy light. Of course, we don't want blue light to sort of illuminate our homes and businesses. So what the blue LED is, and really where the innovation is that the blue LED is coated with an inorganic material called a phosphor. And the phosphor absorbs this blue LED and converts it into a broad spectrum. And so the way that we are able to create white light and different colors of white light is by different blends of the phosphors. And so that's really what my group is working on, is how do we make new phosphors that allow us to hit different colors. So Shruti, I know you've done a lot of background work on sort of what phosphors are out there today. What are you seeing?
Yeah, so mostly for lighting, like general illumination light bulbs, we have the prototypical yttrium, lutetium, aluminum, garnet phosphors, so yttrium, aluminum oxide materials. And so when you take that material and you put a little bit of cerium in it, then you get this yellow luminescence. And so, like Jakoah said, you take this blue LED chip and you put on this yellow phosphor, the phosphor will absorb that blue to create yellow. And so then when you take a similar red phosphor, like strontium silicon nitride or calcium aluminum silicon nitride, and you put that with blue and yellow, now you're covering the majority of the visible spectrum. And so the blend of that blue and yellow appears as white light. And then on the flip side, if you're going to talk about a TV and displays in that way, we also use phosphors there and blue LEDs, but you use slightly different materials because you want better color purity of those phosphors. So we use green phosphors like beta Cylon, and then a red phosphor like potassium silicon fluoride.
So you're saying what you're doing is making the chips better, the LEDs better, but does that mean they're more efficient because of that?
So yeah, so the process of conversion is always a lost process, right? There is no free lunch. So when we take this blue LED, which has a high energy, and we convert it to a lower energy, there is sort of a natural loss process in this sort of energy conversion. And so what we want to do is make sure that every photon that is absorbed, or as many photons that are absorbed from the blue LED, are converted and re-emit this different wavelength. And so by efficiency, yeah, we're really looking at how do we do this as how many photons in, can we get that many photons back out? If we absorb 100 photons coming from the LED, we really want 100 photons back out, just because of the way these materials are made. An industry material today will get 95 back out, which is still pretty good. But you can imagine that in every light fixture in the world and every LED chip in the world, those 5 lost photons, they add up. And so we want to see how do we get to 96, 97, ideally 100% conversion. And that's where the efficiency comes from.
Yeah, sorry, I was going to say a lot, and getting those 5% of those photons out is based on the phosphor side of it, not on the LED side. So we have to take these materials and either optimize the ones that we have or discover brand new ones that do this process more efficiently without as much optimization.
In the past, electric lighting was a function of some kind of combustion, no matter what the light source was, right? So there was actually a burning going on. Is there any combustible processes that are happening with these LEDs? Is it a completely different type of way that it works?
Yeah, it's a fundamentally different process, and that's actually why they get the name sort of solid state lighting. So if you go to either read in the literature or even in any sort of explanation, they'll always be called solid state light bulbs. And the reason is every component of it is a solid. So the indium gallium nitride is it's a semiconductor, just the same way that all semiconductors are used in switches and anything in computers. It just happens that the indium gallium nitride emits blue light. And then these phosphors are solid state. So yttrium aluminum garnet is a naturally occurring mineral that has been sort of, say, reapplied in terms of the LED lighting. So there's no moving parts. There's no burning. There's nothing that's happening in that way. But because of this, that's why you get these really generally mechanically robust light bulbs that are, largely impervious to dirt. They can be easily placed into, at least with proper sort of encapsulation, humid environments. They're really able to withstand a lot. In fact, the fail point, so one of the things that people often, sort of complain about or run up against is that LED lights are sort of touted as, lasting for 10 years or 15 years. So you go to the store, you buy a light bulb, and you assume you'll never have to replace it again. And it turns out that you probably have had to change out one of your LED light bulbs at home, and that tends to make a consumer mad. It's not actually the materials. It's not the semiconductor that breaks. The phosphor doesn't break. These things are literally rocks. It's always the solders, right? It's the leads that connect. It's cheap manufacturing, to be honest, where these leads just break, and if you were creative enough or clever enough or willing to, you could probably open up your light bulb, take out a solder gun, reconnect the wires, and your light bulb would turn right back on. So it's not a materials issue, it's a manufacturing challenge.
There is deterioration though. There is lumen loss from the LED array for sure, and so that does occur. But in terms of the cheap manufacturing or not, I've been in this game for a long time, and we support Satco and all this sort of stuff, but it's really difficult to know who actually knows how to make this stuff the best and who doesn't. I'll be honest with you.
Yeah.
And sometimes price is not in the market is not indicative of higher quality. Sometimes it's indicative of accreditation agency's label on the box, which may have nothing to do with quality at all. Let me ask you: are any of these chemicals toxic?
So we often will write that they are non-toxic, but it's hard. I mean, so they are not toxic like compact fluorescent bulbs. I can 100% say that.
So there's no mercury. There's no mercury.
There's no mercury. There's nothing.
No mercury.
There's nothing like
usually
that.
lead free.
Okay.
Yeah.
Yep. Yeah, except for maybe the solders. I would imagine a lot of these manufacturers are using lead-free solders today, which, to be honest, may be some of the issues with some of the solder welds. But it's hard to say, right? I mean, in a commercial scale, all of these are, purified elements. Indium gallium nitride on a geologic timescale
sounds toxic.
Right?
Sounds toxic.
Sounds
to
toxic,
me.
right? Hard to say. Hard to say.
Yeah.
But compared to compact fluorescent bulbs, no, you're talking about toxicities that would probably be the equivalent of an incandescent bulb, right? I mean,
Sure.
Is a tungsten wire toxic? Not really. But is it great to have tons of pure tungsten around? Well, probably also not really for other reasons.
Well, the reason I ask is that while CFLs and mercury vapor, mercury lamps are something we want to sunset and we want to get rid of. There's a push to get rid of them maybe quicker than I think is really healthy for the industry and for that. But we know where the end destinations of this stuff are. So I recycle millions of lamps every year. And they end up at a facility where the mercury is captured. Most of it is captured, and I've been there. I can see the drums of mercury. They've showed me them. I've watched them process the lamps and all sort of stuff. And we certainly don't want millions of LEDs going to landfill. When they burn out. So that's the reason why I ask. In terms of these coatings, are these like when I hear what you're talking about? I feel like you're putting like a micro lens on top of something, or like a chemical lens. Is that a good comparison? Either Shruti or Jakoah, whoever wants to take that one.
So, I mean, it is kind of like a lens, right? It's more of like, we call it more like a cap, because you have like this flat LED chip, and then you take this phosphor, and usually you will encapsulate it in something. Correct me if I'm wrong, Jakoah, I don't think it's a direct contact between the LED and the phosphor. Usually there's like an epoxy in between the two. And then you just literally layer them on top of each other. And so once you have them on top of each other, now you won't see any of the blue light from the LED chip coming out, because it's mostly getting absorbed by the phosphor, and then the residual blue and that phosphor is what makes that white.
And so are we at...
They're not... Okay.
Go ahead, Jakoah. Yeah.
So they're not... Yeah, so they're not... Like a lens, I would think of something that's going to help shape the light or change sort of the directionality or the polarization of the light. This is more, it'd be almost like if it's just a conversion layer. So it's more like if you were just take a plastic coating and put it on top of a normal white light bulb. You're just doing that for blue and converting the light in that way. So it's more in some ways it's like a filter. It's more like a filter in some ways.
Filter, yes. Okay, that's a better word. That's more of what I was thinking about when you said that. Like it's filtering the light through a process that does the light actually change? Like is the light?
Yeah, it does.
It does? Okay. How does it change the light?
So this is just the process of fluorescence. So there's the way, and this is the way that all fluorescent materials work, is that you have some incident photon of light. So a photon of light comes in, and then you have, and this can be, in this case, these are solid state materials, but molecular compounds work the same way. They absorb just like just like any molecule can absorb light. And then the molecule has electrons that absorb the energy coming in, and they're excited into the excited state. And then you have a couple processes that can happen from the excited state molecule. Either it can do what we call non-radiative relaxation, which is essentially just generate vibrations, which is heat. So this is, for example, what happens when a tile in the sun gets hot and you go outside, maybe next to your pool, and you step on the hot tile, you burn your foot. Well, these have been absorbing photons coming from the sun. The process then of how the energy gets released is by vibration or heat production. So that's not what we want, right? We want to produce photons. So we want radiative relaxation. And so there's different ways that you can sort of drive radiative relaxation, which is once you excite the molecule or solid can then relax back down. And this change in energy processes always has to be conserved, right? These are some of the fundamental laws of physics. And how you conserve energy is by the release of a photon. So depending on the energy transition from a ground state to an excited state, if they are closer together, that's a narrow gap, which would be a low energy light, which would be like red light. And if the gap is really big, that's going to be more like a blue light. And then anywhere in between. Really big is ultraviolet. Really, really narrow is near infrared.
Well, there's a lot of talk about near infrared.
Yeah.
Right now, we just did a podcast on it recently. Let me ask you. So we're taking electricity, we're turning it into electric light. We want to commoditize that and make that more efficient. Who is funding your research? Like, what kind of, or is there any corporations or any manufacturers that are interested in what you guys are working on?
Yeah, so I'm funded very generously by the National Science Foundation. So we have a few grants to support this research. I'm also, so at least somewhat indirectly for this project, a fellow of the Alfred Sloan Foundation. So the Alfred P. Sloan has fellows in chemistry and physics, and they're supporting sort of our effort towards developing energy efficient lighting. And then we have, I would say, connections, not direct collaborations, but we're constantly talking to lighting manufacturers. So we recently wrote a paper with some folks from General Electric at their global research center up in New York, looking at Niskayuna, New York, looking at how do the chemical stability of phosphors change, right? So thinking about when we make these types of devices, as Shruti said, you take the phosphors and you put them into a silicone epoxy, and then you drop cast that on the LED chip itself. So there's water exposure, there's all sorts of chemical exposure. What happens to the phosphors? How do we maximize or rather minimize changes to the materials? As you said, there's lumen loss, right? So how do we minimize lumen loss? Of course, this is happening because of exposure to the environment. Houston is a harsh environment. Toronto is a different type of harsh environment. How do we make a device that's going to work in both places? And so looking at accelerated aging tests, stuff like that. So that's what we've been working with that team on.
Nice. Now, kind of going back to some points you mentioned earlier, the LED itself, the components that go into it, I wrote them down. I want you guys to tell me if I'm off on it, but there's an LED chip, there's a phosphor, there's solder points, and there's epoxy. Is there potential in a circuit board? Is that what you call them, circuit board behind it? Is that everything?
A driver. Yeah, a driver. So it's the same driver that you guys are dealing with on say downlights. But yep, that's basically right. And then it depends on what sort of format it's going on. Yeah, Shruti.
And there's usually, if I understand correctly, I think there's also a heat sink, because the LEDs, whenever they operate, they generate a lot of heat in the devices. So like Jakoah was saying, when we consider chemical stability, if we're putting a phosphor on top of a very, very hot LED chip, they can reach like 150 degrees Celsius. Then that phosphor and the epoxy has to make sure that the phosphor stays just as bright at those really harsh temperatures. And so usually the devices also contain a heat sink so that the bulb itself doesn't feel hot like the incandescent bulbs used to. These bulbs get not hot.
Yeah, but when I'm looking at just the LED portion, I know the heat sink and the drivers are part of the bulb.
Gotcha.
Just the LED. That's everything?
I think so.
Okay.
Yeah, basically, and then depending on the format, you'll have different lenses, right? So if you're trying to shape the light to do anything, but again, the optics
Sure.
are sort of in the LED chip itself. How do we make the white light? It's honestly a brilliantly simple design. I mean, it is a blue LED, one or more phosphors. So in today's lights, there's going to be two phosphors. So it's like Shruti said, it'll be usually this yellow, green, and then a red emitter. But you can get away with just blue and yellow, and then the epoxy, and then the wiring to wire it all up, and that's it.
And you mentioned that, or wiring or solder points, that's oftentimes what breaks. So is that how you can measure quality easily? Is like how thick the soldering is?
Possibly. I mean, this is largely just sort of through my experience, discussions, and sort of trial and error failure. I mean, there is no, because there are no mechanical moving parts. There's nothing else that can break. Now there are chemical reactions that can happen. So if we were to throw the LED and those parts into a bucket of water or acid, yeah, you're going to have other problems. But in a general operating environment, yeah, I mean there's not much else that can go wrong. Everything is just basic photophysics that I teach to my sophomore undergraduate chemistry majors.
Here's the question. Okay. Right now we have a problem in the lighting industry with LEDs changing color drastically. Okay. So I don't know if you've seen the purple street lights that are making an appearance all across the United States. And then there's other lights that I've seen where they go from, say, 4,000K to a bizarre color of yellow over time. That it's like it's transitioning. What's happening chemically to cause a light fixture to go from 4,000 Kelvin to purple? What would cause that?
Yeah, that's a little bit back to this work that we were doing with the team from GE. It's it's going to be a combination of things. Largely, it's probably that well, it depends on the design, but largely I think the phosphors are probably just degrading in their ability to convert, right? So you can imagine that even if you did this, right, if you took out, let's say I don't know, maybe you guys have a couple iPhone 14s to spare. If you take and take the flash out of the phone, take the phosphor coating out, you're gonna have just this blue LED, right? So same thing, if the phosphor starts to degrade for some reason, right, be it environmental exposure, maybe poor encapsulation, then you're going to get some of these color shifts. And so that is what we're trying to look at, is how do we stop this from happening? How do you prevent or make something that's naturally chemically robust? It doesn't need to be maybe encapsulated. It doesn't need to have protection.
Are there varying degrees of quality in the phosphor itself? I would assume, but I guess that's what I'm trying to figure out. Is everyone using the same basic phosphor and just putting a varying amount, or is it totally different phosphors?
Yeah. So it depends on. It's a little bit different phosphors. From my sort of vantage point, there's probably only about a dozen phosphors commercially available today. Now, like you said, it depends on who the phosphor manufacturer is. What's their QC/QA process look like for suppliers of raw material? What's their more downstream processing look like? Are they encapsulating? Meaning they take the phosphor and maybe they put like a glass coating on it so that it's going to be more chemically robust. There's lots and lots of additional, not I will say components, but additional work that can improve the reliability of these phosphors. And so that's, I will say, in my opinion, from an individual sort of commercial standpoint, so not a commercial user, but just from going to the store and buying a light bulb, there is a lot that goes into, or a lot of value in buying the more expensive light bulb, because they tend to be using the more expensive LED chips. They're going to have a higher QC, QA on the product line, and the materials and the phosphors themselves are probably going to be higher quality. So
Maybe not.
I would say generally, right? I mean, the name brand people are probably doing it a little better, but there's probably a sliding scale.
There's a lot of tough talk. Okay, There's a lot of tough talk in the industry.
Sure.
I'm serious about like quality and stuff like that. And we can't find anyone to tell us what's going on with the purple lights, you know? And we've asked a lot of people, why are these lights turning purple? And they, you know, just like you, they haven't specifically looked into that problem perhaps. And then they say it could be this, it could be that, it could be this. But I want to know, how do you go about creating a purple light? After it was forth, like what would be the like if you wanted to create, if Shruti and you guys said, okay, I actually want to create this, there obviously is chemical reactions going on, whether it's that's heat or water, something's getting in there and creating a chemical reaction and turning this stuff purple. And then how do we stop that from happening, you know, to these LEDs? And you know, it's a serious, because this is critical infrastructure. Okay.
Yeah.
It's not. They're not there for Halloween. They're not there for fun. They're, you know, there's you know, I'm involved in a lawsuit now with a vehicle accident. Okay, and you wouldn't believe what the lawyers pull out in terms of these regulation books on how the lighting is supposed to be and how the crosswalk is supposed to be built and all this sort of stuff. And so there's a lot of regulation violation going on with our critical infrastructure with respect to LEDs dimming over the course of their lives, and changing color and this sort of stuff. And you know, would you suggest that purple is a phosphor color? The blue?
Oh, no.
What is it?
I think it's the blue. I think it's the blue itself. If I had to venture a guess, I would say that something like the phosphor coating has probably delaminated off the LED chip, and so you're seeing basically a lot more blue light coming through than what should be there, right?
So blue is purple.
Color,
blue is like
so it's hard to say, right? Is it? Yeah, I mean, you're looking at so it's just your standard color, like rainbow color, right? Roy G. Biv. So it's going to be violet and then blue. So they're right next to each other on the color spectrum. So is it truly a violet color? Well, it's probably sort of a failed mixture, like Shruti said. It's you have your blue component, your yellow component, and your red component. If you pull out the yellow component, what you're left with is blue and red, right? And what does blue and red mix to make? Violet light, or purple light.
Purple light. So like, that's to me, that's when someone says, you know, LEDs last a long time. I think, you know, what we have to look at is how long, and they have these different metrics that they have out there in the industry to measure this, and it's done with accelerated testing. But how do you say, like, you know, that purple light is actually still working? Like the LED is still working and the driver is still working. We just have some crazy purple. Like, it's pretty spooky. I don't know if you've seen any of the pictures. I can send you some that have come in. But, you know, I think that's actually at the chemical level, in my opinion. There's no way the optics could have done that. There's no way anything else could have. That LED is emitting a purple violet light for some chemical reason. Right. And we need to get to the bottom of that, because we're not that far into this LED revolution. You know, we're only really 7, 8 years into it. Are all the lights going to start to turn purple eventually? You know, what's the end game?
So I think that this, you have to kind of, I think if you sort of take and certainly it is not an ideal light, but that's where if you say, is the LED failing? Again, it's not, because it's producing light. Yeah. You know, when a light bulb fails, when an incandescent light bulb fails, when a sodium vapor street light fails, they don't work anymore, right? So it's a very obvious, it works or it doesn't. In this case, it's just not producing what you want. And so I'm confident it's not a materials issue. It is a material device design failure. So somehow, again, I would venture a guess, either the phosphors have somehow decomposed. Did they cheap out on product manufacturing? Possibly, right? Possibly. I don't know where they're getting these lights from. I can tell you, I'm at a state institution in Texas. You know, we're not necessarily going with the highest price vendors all the time. So I'm sure that, you know, if a city is changing out their light bulbs, they're not buying the best downlights, right? What are they buying? They're buying the best one that they can put into their project.
I would argue that, you know, again, the correlation between, I've seen really expensive light fixtures fail, and I've seen really cheap fixtures last a long time. And this idea, so the phosphors can actually decompose, right?
Sure. Yeah.
And so, what do you mean by that? What is it falling apart? Is it coming off of it? What do you mean by decompose?
So, I mean, I think it can happen in different ways, or there's different mechanisms that can cause a material to fail. And they all involve either the production aspect of putting the bolt together or during operation. So,
Mm-hmm.
in the production aspect, if you have a material that just absorbs water, right, it can incorporate water into its structure, then that water can cause the color of the phosphor to change. So, a really popular phosphor is this potassium silicon fluoride, and it's the color of, like, the actual color of the powder is yellow. But once you start exposing it to ambient moisture, it starts to turn brown. And then that red light it produces just slowly fades because it just can't produce that red emission anymore. And so that's why researchers at GE, they're working on trying to make sure that they can find an encapsulation or something to prevent that, like browning is what they call it. But other things is like, what if the phosphor just gets too hot from the LED chip? Well, if you heat something up, it can also start to decompose. And so for that, at least on our side of the research side, the research that I do in Jakoah's group, is we try to identify these materials that are inherently thermally robust. Like if you put them at 150 degrees Celsius, we have to make sure that the structure of that material doesn't change and decompose, and that the light it produces is still just as bright at these elevated temperatures. So there's lots of different factors that go into a temperature. Even the light generated by the blue LED, what if it's just the energy from that blue light? It's usually very, very intense because they're very bright LED chips. So how does that like affect the material itself, and then water and things like dirt and stuff like that?
So, but when you say decompose, you're not talking about it's not like a part of the chemical process of the material when exposed to heat. Like you're saying that there's obviously some formula that you could lay on paper that said, if we studied it, this happened, and so eventually you have purple light. That's obviously a chemical process, whether it's moisture or whatever, that's causing that. And I know I'm beating this drum, but I'm very interested into why this is happening, and I'm concerned that it's going to continue to happen more and more.
Yeah, you're right. I will say today, and that's actually one of our more recent proposals to the National Science Foundation to study, is actually what are those products. Okay, so again, I think it's this balance. The purple light that you're seeing for sure is the LED, right? And the reason you're seeing the purple light is because we're losing the other two emission colors. And so, what are those?
Where
products?
did they go? They turned brown, or they did, like, what happened to those?
Well, yeah. So when they turn brown, they just stop emitting light, right? So as soon as the thing, because it's always this conversion process. But remember, like I said, it doesn't have to emit light. Once it can absorb the blue light, but it doesn't have to re-emit the light. It can generate heat, and so that's instead is sort of the relaxation process. And so, just because it's coated on the chip doesn't mean that it's undergoing this photon sort of cascade conversion process. It may simply be what I would call optically dead, right? It's absorbing light, but it's not producing any new light. So what do you see left over? You see the residual blue light. And that may be where you're starting to see some of these, why it's purple or some other
green,
color, not blue.
Green,
right? Because you get a
green.
mixture, right? The ideal spectrum is now contorted because what component you needed has sort of
Failed.
it's failed, right? It's chemically failed, like it has been exposed to air or water and decomposed just the same way that chemicals can whenever you put them in water, for example. Or it's I won't say physically failed, but it's failed because at high temperature it's no longer again producing this conversion process as efficiently as possible. And so that's why you'll see, and this is actually a super popular or super hot topic research area as you start to get into the last one, higher power lighting, right? Think about all the headlights that are becoming more popularized. You're talking extremely bright LED chips to drive, 1,000-meter laser-based LED headlights. These things exist. The phosphors that are needed to keep up with that much incident light are tremendously different than what are needed in streetlights, but they're still using the same materials, just in different architectures to try and account for it. So that's actually what we're doing, right? We're looking at how do we make these new materials that can, instead of, that can, because today the same phosphors that are in your computer that you're looking at right now are the pretty much the same phosphors that are in your street light, that are pretty much the same phosphors that are in your GE light bulb at home, and they're pretty much the same phosphors that are in laser-based headlights. There's not a lot of materials out there.
So your
So
image right
including
now
them.
you're generated by phosphor. That image I see there of you, it's
Yeah.
generated by phosphor. That's crazy. Okay,
Yeah.
so
Yeah,
Greg, I think
depending on your device. Yep.
yeah, it's interesting. The LED lights don't burn out; they decompose, Greg.
Right.
They
Yeah, that's right.
decompose.
That's right.
You talked a little bit about commoditization, or I wrote down commoditization in the beginning, because what you want to do as a university is that you want to improve things and make them available to everybody, I take it, right? So the process of
Yeah.
commoditization is for us to take really high-end product and find a way to make it cheap so that everyone can have access to it. Is that the correct understanding? And you have a sort of, in your research, you have a mandate to sort of lower the cost of high-end technology?
Yeah. So it's yes. So that's one of the goals. So we're sort of looking, I would say, at new platforms to do the material synthesis, so that the synthesis process at scale is overall cheaper. So making, for example, some of the nitride materials, so the red emission component of the light bulb, they require, or can require, high pressure furnaces, or the green component that's in the display you're looking at. They require these high pressure furnaces. You can imagine that running a furnace at a megapascal. So right now you're sitting at just over a kilopascal. So a megapascal at 1800 degrees Celsius is how they make the green phosphor. There's costs involved in that, right? That's a
Sure.
tremendous amount of cost. So how do we look at materials that don't require these pressures, these temperatures, but still produce the same quality of light? That's really what we're one of the things that we're looking at.
So if you were to measure the life cycle input of an LED, you'd have to factor in all that LED and energy to create the phosphors on top of everything.
Yeah,
That's
absolutely, absolutely. Yeah, so I've served on some panels for the U.S. Department of Energy. They have sort of a roundtable discussion. I think it's every other year that they sort of publish these guidelines and have these discussions. And this is one of them, right? When we talk about energy efficiency of LEDs, the input in growing the LED chip, in making the phosphors, these are taken into account. And so there is certainly value in figuring out how to sort of clean up or simplify that process as well. Again, it's a challenge, because the materials that we're using today, we're using them because they're the best. So it's this balance.
And they're dug out of the ground, right? These are mined virgin materials.
No, these are materials that are all synthetic. So a lot of them are inspired by minerals. So the yttrium aluminum garnet is, if you were to actually take yttrium aluminum garnet and put chromium in it, is that right, Shruti? You would have, I believe you would have ruby, right?
No, that's aluminum oxide with chromium. Is it ruby?
Oh, corundum. Sorry.
They're mixing them up.
Yeah, that's right. So they're close. So, but a lot of these are mineral inspired. So they are minerals that people then have taken, have sort of made as pure material. But everything that's in a light bulb today is synthetically made at one of these manufacturers.
Like BASF would make this kind of stuff, or a company like that.
So I don't. Yeah, a company like that. I think. So General Electric. Well, the company is now. It's a subsidiary now of GE, or former subsidiary, called Current Material Solutions out of Ohio. There is Mitsubishi Chemical in Japan, makes a ton of phosphors. There's a few in the Bay Area. Sorry?
Cree?
Cree does not make phosphors. Cree makes bulbs, but they actually don't produce their own phosphors, as far as I know. So they're sort of scattered around. A large number of the producers, though, I think, are in Asia, Korea, Japan, China, most of all.
Germany,
We have a few.
right?
We
Is
do have a
that
few here
right?
in the U.S. Oh, and in Germany. Yep, that's right. And then you have Osram makes their own phosphors in Germany as well.
I don't know if you know the answer. Are any of these chemicals, are they militarily? Is there like a DARPA aspect to this where they want to make sure that we can make these materials in the United States?
There's a few efforts. So the one of the ways that so the way the light conversion process actually occurs is through rare earth ions. So
Mm-hmm.
the rare earth absorbs the light and then re-emits the light. So the mineral structures that we've been talking about, like the aluminum oxide or the yttrium aluminum garnet, that's really sort of more like a host or a scaffold. So you
Mm-hmm.
sort of just use this, yttrium aluminum garnet itself is white, but once you put and substitute cerium in, it becomes this really nice yellow powder.
Mm-hmm.
Yellow because it's absorbing blue light from the sky, and then when you irradiate it, it produces the yellow photons that we want. So there's a good effort in looking at how do we maybe make these with less rare earth or fewer rare earth or more, let's say, domestically available rare earths. So that's one of the aspects, at least in general lighting.
There's
Now I think
also,
where you're oh good.
sorry, I was gonna say there's also new efforts that I've been reading about how is once these light bulbs, like once we stop using them, can we also extract those rare earth, like the cerium, back out so that we can repurpose it again?
Mm-hmm.
Right.
Yeah,
Yeah.
I've heard that from lamp recyclers that it's very difficult to
Yeah,
get the rare earths out of the phosphor powder from
it is.
it's almost more, it's better, easier to dig it up.
It is.
The Yeah,
Yeah.
what's interesting is that, and what I'm hearing is that these light fixtures that we have with these LED strips in them, Greg, they have a chemical construction to them that over time the wheels start to fall off. Like little parts of them break, of these little tiny little structures. And, that's called decomposition. This is what I'm learning from this show. And as these things decompose, that's the LED failure. It's not that there's a filament inside that cracks and the light turns off. It's that these tiny, tiny chemical machines that we've built are starting to come apart. And as they come apart, the light changes, or the light output gets reduced because of the browning, or it turns purple because the chemical structure of these things fall apart. And I think and just in listening to you guys, it makes a ton of sense. I think manufacturers are way, in the beginning especially, have way overestimated how long these little chemical machines can last.
I think that's right. So I think as I say, so there are also the ones where they just totally fall apart, right? So where the solders
Sure.
do break.
Sure.
But the color change, you're 100% right.
Yeah, it's like
That's-
the wheels
all
fall.
their-
that's
all-
the- Mhm.
All they're measuring is the LED chip itself and not everything that goes along with it, right?
Yeah.
Well, I mean, people do like accelerated aging tests, right? Where you can put the material in this chamber that controls the temperature and the humidity at the same time, and then you can track and see, like, how does the color change. And so there are standards that have been developed that basically, I mean, even the Department of Energy states, like, this is how much the phosphor color can change before it's no longer acceptable. And so there are goals that the Department of Energy has stated, like, this is the amount of color change we're going to allow a device to have before it's no longer acceptable. And the only way you can track this is with these chambers. And then you start running into a lot of variables of, like, well, what's the mechanism causing this? What is the insulation layer to stop this from happening? And so that is a lot of the research that's being done in order to minimize this sort of failure and the color changes that go along with it.
Yeah, there's no way, though, to accelerate anything. That's not possible. You know what I mean?
Yeah,
That's that's a robustness test or something. That's all it is.
So they,
You know.
so they, it's not exactly field deployable, right? These are pretty clean environments. It's not
Sure.
South Texas or West Texas in the dirt. But I think it's also worth noting that even if companies in sort of their device construction and device testing, these are guidelines, right? These aren't requirements. They're not they're not required. There's no certification from the DOE, as far as I'm aware, that says you have to fall within this minimal color change, right? These are just saying for best practices, here is what you should be looking at. But that's, yeah, I think you're right that there are many mechanisms for failure when you look at a subset of a few lights and a few grams of material into a light bulb versus an entire production line of devices coming off.
Yeah, I think it's accelerated testing is a I have I find that very interesting. I actually do some work at universities in growth chambers for plants, and they're trying to mimic different types of environments in the real world and all this kind of stuff. But it's really somebody's making a decision of what I want to test, if the humidity is higher, or if the heat is higher, or if this happens over this period of time, I'm going to measure what's going to happen and I'll extrapolate it out, using some kind of a model. And I think the industry went a little wild with those and maybe said some things that they really didn't know what they were doing, Greg, in the beginning. You know what I mean?
Yeah, and I think that's where we're at now, and it sounds like you guys are, trying to improve on that and make LEDs better, which we need. So thank you for that. Keep doing it.
Yeah, keep doing it. And if you ever figure out what's going on, like exactly with those purple lights, we really want to know. But what I do know is this: it's unrepairable, right, in the field, at least, or anywhere.
Right. Absolutely. Absolutely.
And let me ask you one more question. Actually, just occurred to me right now. Just as there is no way to withdraw the component rare earths out of phosphor powders, for example, they store them. I've seen them stored where they're storing the phosphor powders. There's no way to recover any of these elements from these LEDs when they die. Like it's garbage. Is that correct?
So there are efforts this way. Today, I would say it's certainly still cheaper to throw them away and put a new device in. But this is something that people are looking at. How do you get the phosphor back out of the epoxy encapsulation? How do you recover it? So not even necessarily recover the rare earth, but recover the components in the phosphor. As far as I'm aware, that this is sort of on the radar of something that people are looking at and working on, but I think that's still in its infancy.
But also, like, once these materials are decomposed, in my opinion, there's no getting them back out to their former glory. Right. Like you can't take this material from a decomposed state and make it back to what it once originally was. That's gone. There's, saving that.
So LEDs are unrecyclable.
From the phosphor component, maybe. I don't know.
Sure, and from the indium gallium nitride. Again, no, I would say similar to trying to recover the rare earths. Indium is very much a precious commodity. For the amount of electronics that we have, indium is used in a majority of, not even a majority, all touch screens use indium. Blue LEDs use indium. There's a huge drive to try and figure out ways to recover this indium. I think it can be done. The science is there. The question is always, can it be done at scale to offset cost?
Wow.
If it's cheaper to produce new, people do that, right? And that's where you have to have kind of a, what's the value add in the recycling process? Is if it's going to make your device more expensive, are companies going to want to do this and cut into their bottom line? I'm not a company man, but I'm going to go ahead and say the financial folk would probably advise against that, even if you could do it.
I've never ever I don't care what it is. I've never once seen a plan of a real, like, this is what happens at the end of the life of your product you just bought. And we already know that in advance. It's always like we make this stuff and then we figure it out as we go along, Greg Eric. But if you're a lighting guy, Greg, where you can figure stuff out as you go along? At satco.com, baby. That's satco.com, man. Those guys got everything.
That's right. We talked about at the beginning how you find new product every day with those guys. 15,000 some items.
Yeah, I got lots of items, and we really, the good people down there in New York. I think they have 4 warehouses around the United States anyway. But they're great company, satco.com. Love the people there, and of course, Greg, the National Association of Innovative Lighting Distributors. That's NAILD.org. America's Lighting Convention's coming up in September. That's right. We're going to be visiting the Dallas Cowboys Stadium. Is that what it is, Greg?
That's right. Yeah, stadium and owner's suite tour.
Woo.
Check it out.
Fun. And of course, thank you to Shruti and Jakoah for being on the show today. And of course, you, the listeners out there in lighting world that keep up with us. Hey, we love you guys. Bye for now.